Alright, so we are in week 3 of the NPTEL course on urban utilities planning, water supply, sanitation, and drainage. It's a live session where we discuss a few problems that we suppose that will help you in solving your graded assignments, as well as will help you with some general insights. So I'm Monica S. I am a PMRF candidate and a research scholar at the Department of Architecture and Regional Planning, IIT Kharagpur. As usual, we have two means of having interactions and clearing doubts here. One is this session every Monday, 7 p.m. to 8 p.m. After every question or every couple of questions, I would prompt for you to ask questions if there are any, or if there are any queries. You can just raise your hand. There is an option in Google Meet. You can see it at the bottom of your Google Meet screen. You can unmute and then raise a query. Or if you're uncomfortable or unable to, raise a query verbally, you can also post the questions in the chat box. Apart from this, we also have a discussion forum where any questions related to the live sessions can be asked. Uh, you can also ask questions about the regular sessions for which the NPTEL core team will respond, the team for the original course. Questions that are raised there that are pertaining to my sessions, they'll either be addressed in the forum or in the next week's live session. That being said, in the last session, someone had raised a query about the first graded assignment for this run, and I raised the query with the team. They said the questions, the answers given are correct. So I would request you to rework on your graded assignment. Also, I think the answer keys for the first and second assignments are out. So you can check out the answer keys and figure out where you have gone wrong. Queries regarding those can also be raised in the discussion forum. So a small recap. Week 3 had 5 lectures, module 3. Uh, the first one was on rainfall, runoff, and groundwater. Then groundwater properties and flow characteristics were covered. Groundwater intakes and issues was covered in lecture 13. 14 included groundwater yield, where a couple of numericals were solved. And lecture 15 had surface water intakes. So in the current live session, we'll be mostly looking at problems from the previous run of the course pertaining to week 3. However, if time permits, then we can also look at a few questions from week 0 assignment. The thing is, the video for week 0 is actually available on my YouTube channel, but I don't think it was made mandatory. So they are very basic questions, and they're very introductory. So the ones that are related to this lecture will be handled here. So let's dive in. I think it's 7:05. So we'll just start with the. Before I start, were there any general queries in the interest of students who might be joining late? And since I'm starting with a numerical, any general queries regarding week 3 lectures? Right, I don't see any prompts. You can also post it in the chat box, which will be taken care of later. So let's start with question 2 from the previous run of this course. A real estate project on a 15-hectare site contains 8 high-rise apartment buildings, each with ground coverage of 2% of the site area, and houses a residential population of 18,000. 40% of the site area is for landscape gardens and parks. The rest of the area is for roads and open parking. The site experiences rainfall of 1580 millimeters annually. Assume coefficient of runoff for landscaped area and roads or paved area to be 0.15 and 0.65 respectively. The average surface runoff from the site after heavy rainfall of 150 mm in 2 hours, corrected to 2 decimal places, is. So the thing about this question is we don't actually need all of the data that is given. We might not be using, for example, the residential population or the annual rainfall, because what we are calculating right now is the average surface runoff for a particular rainfall event. So, say there is a rainfall incident, say today evening, earlier today, 6 p.m. to 8 p.m. rather, 5 p.m. to 7 p.m. We had 150 mm rainfall on the site. Is what was that was the incidence of rainfall, and that was one event. We are going to calculate how much runoff are we supposed to expect from this site. And runoff, mind you, it's surface runoff. Can you expect from the site? So moving on into the lecture has a couple of slides on runoff, surface runoff, and runoff determination. So we'll be using the rational method. So there are several empirical formulae for determining runoff, but rational method is something that we use very generically in without having to worry about the particular context or the rootedness. So this is something that is generally acceptable in the discipline. So these are our given facts. Site area is 15 hectares, population of 18,000. Ground coverage, we have 8 high-rise apartments with 2% coverage each. Gardens and parks have 40% coverage. Roads and open parking cover the rest of the area. So then we have annual rainfall of 1580 mm. The runoff coefficients are given in the question. So you can see the runoff coefficients, the general values have been given here. So usually the more permeable a surface is, the lesser the runoff coefficient. So what happens is when your surface is very permeable, or it allows for seepage into the infiltration into the ground, what happens is the amount of surface runoff, so the amount of water running off on the surface literally would be reduced, because there will be losses due to seepage. In fact, take something like a forest area or some surface with grass. What will happen is these vegetation, these components sort of slow down the flow of water, which means it's not just the permeability of the surface, but the amount of time or the velocity that the water has is lowered, so amount of time that it spends on the surface is increased. Therefore, again, we are going to have water seeping into or infiltrating into the ground, which is why the runoff coefficient for forests or vegetated areas is very low compared to a concrete paved area where water tends to run off. From personal experience also, I think we understand the fact that wherever it is paved or where we have roads, the amount of water that is gushing through is quite high. So those are we have been given runoff coefficients. Landscaped area we've been asked to take 0.15, and roads or paved area is 0.65. So the current event of rainfall, we have 150 rainfall in a period of 2 hours. So what are we supposed to find? The average surface runoff from the site. So for the calculation, we'll be using the rational method. Q is equal to C into I into A divided by 360. So what is Q? Q is the quantity of stormwater discharge in meter cube per second. So the units are very important here. Whenever you, as is understood with any formula, we need to input all our data in the appropriate units for us to get the correct answer. Otherwise, we could be off by quite a bit. So yeah, so C is the coefficient of runoff of whatever surface is being calculated for. I is the intensity of rainfall in millimeters per hour, and A is the drainage area in hectares. So first of all, what we'll be doing is we realize we have a site and we have a few buildings on it, and vegetation and roads or paved area. So the first understanding in this kind of problem is whatever is collected on the roof. I hope there are architects, civil engineers, or planners. You will understand that what we do is we design, drain pipes from the roof so that we can drain it off into the nearest stormwater drain, or in case of a combined sewerage stormwater drain network in the city, we make sure though we let it into that combined network. So it is we don't expect runoff from this quantity of water. So whatever is falling on the roof of the buildings, what will happen is they will be collected and they will be sort of directed into the stormwater drain or whatever drainage network that is going to be applicable for that particular site. However, so what will constitute runoff? What are we supposed to expect from the site, as surface runoff without being directed in any way? One will be the landscaped area, and the others will be the roads or the paved area. But if you look at the kind of data we've been given data on high-rise apartments, the buildings coverage, as well as gardens and parks. But we have not been given the area as to how much roads and open parking is. So we've been just told that the rest of the area is roads and open parking. So what we'll do is for the calculation of drainage area. First, we calculate the drainage area, built area will be drainage area. First, we calculate the area covered by all the buildings. So, built area will be number of apartments into built up area of each apartment. So, which is equal to ground coverage into site area. So, built area currently we have 8 apartments and 2%, which is the ground coverage. So, 2 by 100. One second, I will just open my hand. So ground coverage, which will be 2%, which is 2 by 100 into 15. 15 is the total site area that we have. So, which comes down to 2.4 hectares. Then we go on to calculate the landscaped area. So it's been given that landscaped area has a ground coverage of 40% of the total site area. So 40% is 40% of 15 is 6 hectares. Then we go on for the area for roads and parking. So we've been said that it is the rest of the area. So we take the total area and then subtract built area and landscaped area from it. So we have 15 minus 2.4 plus 6, which will give us 6.6 hectares. So we'll be primarily calculating the surface runoff from landscaped area as well as areas for road and parking. So surface runoff from landscaped area, say call it QL, is C into I into A divided by 360. So what is C in our case? C is the coefficient of runoff, and the question says that for landscaped areas coefficient of runoff is 0.15. Then we have I, which is the intensity of rainfall in millimeters per hour. So from the data that is given here, we calculate I as 150 divided by 2. So you get 75 mm per hour. So that was the intensity of rainfall. And A, from the previous slide, it came down to be 6 hectares divided by 360. So when you calculate this, you get a quantity of 0.19 meter cubes per second. Similarly, we calculate the surface runoff from roads in the paved area. So we use the same equation. We're calling it QP for convenience. So there is no hard and fast rule as to what you name these things. So C is 0.65 into 150 by 2. 0.65 is given here, roads and paved area runoff coefficient. 150 by 2, again intensity of rainfall calculated from the data given. And area is from the calculations that we did earlier for the drainage area. We divided by 360. Is there a question? Is there a question? You can ask now. You can unmute and ask.
No, it was by mistake.
All right.
I'm sorry.
Yeah, no problem. So then what happens is we calculate QP to be 0.89. So the total surface runoff from the site will constitute only the surface runoff from the landscaped area and the roads and paved area, which turns out to be 0.19 plus 0.89, and the answer is 1.08 meter cube per second. So which is option A in the given question. Any doubts on this problem? It's a very straightforward calculation. So people might ask, what about areas where there is no drainage and people really haven't given a pipeline? So you add the build. building area also. However, it's standard practice in any building, even those that are non-designed, to have a pipe that connects to the uh, nearest drain. However, again, in small residences, what might happen is they might just drain it into the site. So when that happens, you calculate, you add the area into it. So this is for a very, very specific case. Right. So let's move on to the next question. The major chemicals found in groundwater include calcium, magnesium, chloride, sulfate, or iron, magnesium, sulfate, lead, lead, calcium, fluoride, arsenic, chloride, fluoride, or nitrate. Can anybody answer in the chat box? Yes, I see a raised hand. You can unmute yourself. Shripad, right?
Yes, A, madam, A.
Yeah, okay, yeah. Thanks. Yeah. I think Tamanna also has texted in the. You can post in the chat box if it is just the answer. If there is a query, please. Okay. So Inderjit says C. Alright. Any other answers? Okay. So let's see from the slide that was there in our presentation. So this is the slide it talks about uh, elements or chemicals found in groundwater. So 99% solute in groundwater comprises of 9 major chemicals. So we can see that it's sodium, calcium, magnesium, potassium, bicarbonate, chloride, rather bicarbonate chemicals, chloride, sulfate, nitrate, and silicon. So some of these are elements and some of these are salts. So you can see that from this table also trace elements are those that are very rare and major elements are the ones that are prominently present. So if we look at the answers that are present here, again let's go from the reverse. So here the issue is with arsenic and fluoride. So if you notice here, arsenic is a harmful chemical which is present in trace amounts, which means we don't really want it to go beyond a particular point. So we have already one out. So this option is invalid. But also fluoride is also something that is present in relatively trace amounts. So then with option C, lead is something, lead and arsenic and fluoride. Three options are found in trace amounts. So that is also not our answer. B, iron. So if I'm not wrong, iron is also a trace amount, trace element. Lead is also a trace element. So that brings us to A, calcium, magnesium, chloride, and sulfate. If you look at the list that is given here, which is sort of worth remembering, to be honest. So A is our answer for the question. So moving on to the next question. So this is something that looks very complicated, but it's actually just about putting the right numbers in where you need to. So consider the following diagram and the observations made on a 30 centimeter diameter tube well. The rate of pumping is 1500 liters per minute. Drawdown in test well 30 meters away is 1.5 meters. Drawdown in another test well 60 meters away is zero point 0.6 meters. Depth of water in the well before pumping is 40 meters. So, and there are three questions that are asked about this particular instance. One is the radius of the circle of influence, transmission constant of the aquifer, and maximum rate of discharge of the well, which is Qmax. So if you actually went through the lecture, all of these terms should be self-explanatory. However, in the interest of this session, I'm going to quickly brush through at least what the questions are first. So what is this radius of the circle of influence? So This is a slide from the presentation that was there in the past week. So whenever we have a well or uh, any kind of well which from which we are taking out water, pumping out water, what happens is, because you are taking out this water, so this line here is the usual water table. If you're not interfering in the flow of water, say this is the usual water table in that particular area. But however, what we've done is we have dug a hole, we have made a tube well, say, and then we've started taking out water. As a consequence of which, and you know, empirically observed, as well as uh, what has been hypothesized by Darcy's law, if you remember, what happens is there is a cone that forms. So this is not just a triangle in a two-dimensional. Imagine this as a 3D. So what happens is there is a cone that is formed with this point as the center. Uh, this is the shape of the water table once you start extracting water from this particular well. So what happens is, any well or any intrusion here, you will not get water while this pump is active, while you are actually actively taking water or extracting water from this well. So there are multiple methods of calculating this cone of depression or the gradient that is caused. I think all of that was covered in the lecture. But a particular formula that we will be using here, given the kind of data that we have, is the Thien's formula. So it's for calculating the yield of a well. So this is the formula. So let's see what are the values that we have. So this is the formula for Thiem's formula for calculating the yield. So the first component is Km, transmission constant of the aquifer. So Km is merely just a constant here. So what is happening is, when we derive this equation, we club up all the constants into Km. So this is something that is part of the question. If I'm not wrong, question 13, I guess. So we will be calculating this value later. So that's one of the questions that we'll be addressing. So what is the next thing? H is the static head or height of top of water table from impervious stratum. So where is this data given? So depth of water in the well before pumping. So say we are not pumping out water, the water would have stayed at the water table, like the level of the water table, right? So H is this uh, level of the water table or the height of it from the impervious stratum. So the nearest impervious layer is this. So the distance between this water table, the height of this water table from this impervious layer is what is H. So as is given here, it's 40 meters. You can see this arrow pointing out to the extent of the H that we need. So we have H as 40 here in this problem. The next value that we need is a small h, that is capital H, this is small h, that which is the height or the depth of water in well just after pumping. So in case of the main well, so we have three wells. If you look at this problem, they say that the observations made on a 30 centimeter diameter tube well, which is the main well that we are talking about. However, in order to determine this cone of depression or the R value, which is the radius of circle of influence, which is the cone that we just spoke about, uh, which is essentially the area that is influenced by this well. Whenever this well is operating, this is the area, this entire area on the surface is being influenced by this well, which is called the circle of influence. So this cone will have a circle on the bottom of it that will be called the circle of influence. In order to determine that, whenever we install a well, to determine how much is it going to affect, we install test wells in the periphery of the main well. So which are the two wells here? This is test well 1 and this is test well 2. So the values that have been given here, drawdown in test well 30 meters away is 1.5 and drawdown in another test well 60 meters away is 0.6. So essentially for the first well, let's call test well 1 as uh, H1. So H1 is basically the height or depth of water in well just after pumping. So what we are looking for is this height. So if you can look at my pointer. So here it is given, the value that is given is of the drawdown, as in how much is the water table moving down is what is given. What we need is the top of this line, this point versus the impervious layer again. So which will be 40 minus 1.5, right? So that is 38.5. And what is the radius of this well? So the assumption here is that, say you take a very huge well here, which will have a cross section sort of running in this direction. That is the well that we are talking about. So theoretically, the equation talks about the center point being here. So we take this distance of the location of this well as the radius of this imaginary well, say. So R1 will be 30 meters. Right, so this is for test well 1. Recapping again. So we have drawdown, which is how much the water table is moving down because of the operation of this main well, is 1.5 meters. And we have the original height of the water table from the impervious layer as 40 meters. So what we require is the depth of water in well just after pumping. So how much it will start from the impervious layer till the current water line in the test well. So that will give you a value of 40 minus 1.5 here for the first well, which is 38.5. The radius of the well, we are assuming a hypothetical well which is cutting across the entire cone, which means the radius of that well will be the distance of the well from the center of the current well that we are talking about. So this diagram is out of scale heavily. It's for just for representation. So that gives us values of H1 equal to 38.5 and R1 equal to 30 meters. Similarly, if we calculate it for test well 2, can someone tell me how much will be the H2 here? If someone can post in the chat. Essentially,
60 minus 0.6, it will be 59.4.
you mean 39.4. It's 40 meters, right?
Oh, yeah, 40 minus 0.6.
Right. Yes,
59.4.
absolutely right. We also have answers in the chat box from Ashwin and Rahul. Yes, absolutely. 39.4. So I'm repeating again for those who probably didn't catch it. So for the test well 2, it says drawdown, as in how much the water table is moving down is 0.6, which means our height will be 40 minus 0.6. So water table level minus 0.6, that will be 39.4. And we take the radius of this, again, hypothetical well as 60 meters, because the center of this test well is 60 meters away from our current main well that we are talking about. Right. So what else is needed for Thiem's formula? Radius of circle of influence. It is actually one of the questions given. That detail is not available in the question here. Apart from this, uh, rho and k are constants that have been combined into km, so we are not going to consider them. What other data is available for us? One will be rate of pumping, which is q, is given to us 1500 liters per minute, and the radius or the diameter of the tube well is given. So the radius, we are calling this R0 or R0, is 0.15 meters, half of the diameter. So that is the data that is available to us. What is the question? Question number 1. The radius of the circle of influence R in meters is 100, 110, 96 or 130. So this is the data that is given to us. We are going to try to find R. So we'll be using the Thiem's formula for calculation. So say we use it for test well 1. Q is equal to if you see here km, but we don't know the value of km. Km is not given to us. So let us keep it as km here. Is equal to h square, capital H square, which is 40 in our current problem, minus h1 square. Why h1? Because we are looking at test well 1 right now. So h1 square is 38.5 meters square, divided by log to the base 10 of r by r. If you look at the equation here. So what is capital R? Capital R is our circle of influence, which we don't know. We are trying to figure this out, right? So we'll retain it as R divided by R1. So since we're talking about SL1, we're taking R1 value. So then we also calculate the too many unknowns here to be able to figure out. So we have Q is given actually 1500. We have two unknowns here, Km and R. So we can't really figure out the value. So let's figure out what the equation stands for test well 2. So using the same equation, again Km is unknown to us. We take h square to be the same value, which is the water table level, 40 square. H2 is 39.4, and then divided by log to the base 10, R, again we don't know R, and divided by R2. R2 value is 60 meters. So we're basically plugging in all the available values here. Again, we have two unknowns, R and K. So what we do is, we know that both these equations amount to the same Q value, right? So we are equating this, the right hand side of these two. So Km into 40 square minus 38.5 square divided by log r by 30 is equal to Km into 40 square minus 39.4 square divided by log 10 r by 60. So when we simplify this equation, we can take off Km because cancelling on both sides, and then we are also cross multiplying. What we get here is, so we are taking this above and then this below, and I've exchanged the places, so please don't get confused. So when you calculate the value of this 40 square minus 38.5 square divided by 40 square minus 39.4, you get a value of 2.47. Then simplifying the left hand side, so log a by b can be written as log a minus log b. Basic operation on logs. So log 10r minus log 1030 divided by log 10r minus log 1060 is 2.47. Again we cross multiply, and when we further simplify this, we get log 10 log to the base 10 of r equal to 1.983. So we get a value of r is equal to 96 meters. So that's the calculation. Is there any issue with this first question? What we are doing is, we are calculating the Q value, Q formula of Q for test well 1, formula of Q for test well 2, and then we are equating the two because Q value is going to be the same for both. So when we equate the two, we can find out the value of R. Alright, so that's the first question, other question number 12 here. We get a value of 96. So moving on to the next question, we need to find out the transmission constant of the aquifer, which is Km. So now we have all the given values, plus we know the radius of circle of influence, which is 96 meters. We need to find Km. We can again use the Km's formula. Now that we know R, we can just use it for either test well. You can either use the equation for test well 1 or test well 2, whichever is convenient to you. So we have the value of Q, which is 1500, is equal to Km, which is what we are trying to find here. H square is 40 square, minus small h1 square, which is 38.5 square, divided by log of R, which is 96 as we found out in the previous question, divided by small r1, which is 30 meters here. So what we do here is we bring the km here and 1500 here. So what essentially cross multiplying and then inverting it. So denominator goes up, right? I hope it's basic operation, math operation. So when you basically calculate all the values of this equation, you get the value for km to be 6.4. So since it's a coefficient, so always remember none of the coefficients have any units attached to them. So they're always constants. So that's our answer, 6.4. Any queries on this? Again, very straightforward. Once you know which value is what, you should be able to figure it out easily. Alright, so let's move on to the next question in the series. So for the same question, maximum rate of discharge of the well, Qmax is. So we now have two more known values. R is equal to 96 meters and Km is also known to us. We need to find Qmax. So this is the TM's formula, but when will we have this so-called maximum rate of discharge of the well? If you follow the lectures, you will realize that sir mentioned that maximum discharge of well occurs when small h is equal to 0. Basically, at the center of this well, when there is no extraction that is happening right now. So at the beginning of your extraction is when you will get maximum yield, right? So once you're already extracting, the yield might go down. So when the well is unused and then you're starting to pump out, that will be your maximum rate of discharge from the well. That's the logic behind this claim. So then again we use the Thiem's formula for the main well. This time we use h is equal to 0. So finding out Q max, we have the Km value from 13th question. So that is 6.4. Then h square will be 40 meters minus small h square. So in our case, we are taking it to be 0. So it will be 0 divided by log of r by r. So here r will be the radius of circle of influence. But what will the small r be? Basically, it will be the radius of the tube well that we are considering, right? So that will be 0.15. So thus we can calculate these values. You get this value. However, the answers given to us are given in meter cubes. So therefore we divide it by 1000 and we get 3.65 meter cubes per minute. So that's our answer. So any queries on this question? Again, might seem complicated at the onset, but if you just write down the given, what is what, which values what is the data that is given, the first exercise that we did, what is km given? No. What is capital H, small h, what is R1, R2, H1, H2? Then your entire process becomes very easy. Are there any questions? Please repeat last steps to find value of R. Okay, I'm going to explain the R part now. Right. I hope the how we figured out all the values is clear. So these are our givens, right? So I hope this part is clear where we are figuring out. We are plugging in all the values for test well 1. So H1 and R1 we are plugging in. H is for the water table level, and this is for R, the test well 2. So we'll have H2 and R2 values. So then we are equating this and this. So I think the explanation is needed for this part of it. So when you're equating this part, so km into this value is equal to km into this value. What we're doing is, one second. What we're doing is we are canceling. Okay, I can actually take the. We are canceling out these two because they are the same value. So then what I'm doing is I'm cross multiplying. So I'm taking this here, taking this, sorry, taking this here and, okay, sorry, I'm really new to this. So taking the log R30 here and 40 square minus 39.4 here. So you can see we'll essentially get log R by 30 divided by log R by 60 this side, and 40 square minus 38.5 square divided by 40 square minus 39.5 square, 39.4 square. And I've just exchanged the two sides. So I'm keeping all the unknowns this side and the knowns this side. It's merely for calculation purpose. Then what we are doing is we are figuring out this value. It is turning out to be 2.47. Then log 10 uh, r by 30 divided by log 10 r by 60. So whenever you have to the log of a by b, so pardon me, I'm using a mouse, will be equal to log a minus log of b. So we are essentially using this here, right, in the next step. So log r by 30 will be log r minus log 30, and then log r by 60 will be log r minus log 60 will be 2.47. Then what we do is we again cross multiply. So log r minus log 30 on one side, and then the denominator goes to the other side. Then we take all the r values. So this is r, this is our simple algebraic equation. So all the values pertaining to r on one side and to all the knowns on one side. So we'll essentially get log 10r will be 1.983. So when you have a log of a value, to convert it to the regular value, what we do is we take the exponent of the, with the base as the with the value as the exponent of the base value, we calculate this number. So 10 power 1.983 will be 96 meters. Am I clear now? So it's more about the algebra here. It's just equating and then figuring out the value. I hope I was able to clear your doubt. Yes, all right. So that will be our slide. Any other questions on these three numericals? All right. So we'll just move on to the last question from the week 3 assignment of the previous run. Which among the following is not a primary source of water? A. River, B. Glacier melts, C. Canals, and D. Rainwater. So we have a slide in the presentation which talks about primary and secondary sources of water. So primary sources, if you notice, are basically all natural sources of water which you get directly. You are not really putting it in a bottle, or you're not putting it in a distribution system yet. So someone who's taking their water, say in a village, directly from a river and using that water, then they are using a primary source of water. Rather, when you are having Yes, Rahul. Canal is the answer. So when you're having a city that is about to take water from somewhere and then put it in a distribution network, that original source of water that they rely on is a primary source, and the secondary sources are, you know, all the artificial sources of water that we have. So you basically take water from a primary source, direct it through a secondary source, and then it reaches the consumer. So the answer is C, canals. Okay, so let's look at a few basic theory questions from. If are there any questions still now? I hope things were clear. With the numericals, there is one more numerical that's not covered in the graded assignments, but is explained well in the lecture. With almost all the numericals, it's just about knowing which value is what and which equation to use. It's as simple as that. And how do we determine which equation to use? Usually, if you look at the question, you will know what the question demands. Alright, so if there are no questions, let's just go through a few of these questions from week 0 assignment of the last run. We had prepared these questions for a test run for these live sessions, but it was not really made live. So I'm just going to carry forward these questions. They're very simple questions. Which of the following is an example of stormwater recharge structure? So essentially, stormwater is any water from precipitation, which is uh, not like sewage water or sullage water or anything. So, say from rain or snow, and then or a storm, which is where we get the word from. So, we have three options. A is vegetated swale. Vegetated swales are these. Um, yes, Shripad, that's the answer. D is the answer. Vegetated swales are these depression like structures. They actually have a pipe running below them usually, where we allow for better penetration of water, infiltration and penetration of water into the ground. These are permeable pavements where you, instead of just paving the whole pathway, we have these gaps within the pavers. So this is a pavement screenshot of a pavement. And infiltration basins are where you create these depressions and then you fill them with gravel. So gravel have a better potential for infiltration. The water is going to stay here, and when it's staying here, gravel is going to allow for the water to infiltrate better, and therefore penetrate better too. So the answer will be all of these. So runoff is the quantity of water which flows A in sewer pipes, B due to leakage in pipes, C over land to streams and rivers, and D none of these. Can you try answering this, please? One second. Yes, we have one answer. C. Yes, C is the answer. Over land to streams and rivers. So essentially, runoff has three components. So don't mistake between runoff and surface runoff. Right. Runoff is defined as the portion of the precipitation that makes its way towards rivers or oceans as surface or subsurface. So both surface and subsurface flow are calculated as runoff. It's not just the part which is going on the surface. So when we talk about earlier when we were calculating with the problem also, we were calculating something very specific. We were calculating the surface runoff, not runoff in general. So we can see the three components. One is surface flow, which we calculated earlier. Interflows. So a part of the infiltrated rainwater moves parallel to the land surface as surface flow and reappears on the surface at certain other points. So this is basically somewhere between subsurface flow and surface flow. So it has gone below the ground and then it ends up, because of the land formation and everything, it ends up coming above the ground again. So that's interflow. which is also included in runoff, and eventually it will go and mix in either rivers or oceans and subsurface flow. So the answer is C. Yes, all of you are correct. So the next question, just an extension of the same. Which of the following notations for surface runoff is correct? So A, surface runoff is volume of rainfall minus evaporation losses minus percolation losses plus transpiration losses. Or surface runoff is volume of rainfall plus evaporation losses plus percolation losses plus transpiration losses. C, surface runoff is volume of rainfall minus the sum of evaporation losses, percolation losses, and transpiration losses. Or D, volume of rainfall plus all of the above. I think B and D are the same. Right? No. Evaporation losses, percolation losses minus transpiration losses. Right. So what would be the answer? You can type the answer in the chat box. Yes, the answer would be C. So whenever rainfall is falling, there are only three possibilities that can happen. Rather, four possibilities that can happen. One is evaporation, the water can evaporate back into the atmosphere. Percolation is when it percolates, infiltrates into the soil, and then goes further into. So there is a difference between infiltration and percolation. Infiltration is when the water goes into the soil, and percolation is when it moves further down into layers of soil or rock, into subsurface layers or aquifers for that matter. So we either evaporation can happen or percolation can happen, which is water can seep into the ground, or transpiration can happen. Transpiration is when you have water absorbed in the soil, which is taken up by the trees or vegetation, and then it is let off by the vegetation into the atmosphere again as moisture. So we do not calculate any of these when we are talking about surface runoff. So essentially, the total volume of rainfall, and we subtract all the possible losses that can happen to water. Right, and the fourth possibility is it runs off into the nearest river or ocean. So the next question: what is an aquifer? Uh, it's a body of saturated rock or soil through which water can easily move, or it's an underground river or lake. It's a geological formation found on the surface of the earth, or none of these. Any attempts to answer?
A.
Yes, yes. A is the answer. Body of saturated rock or soil through which water can easily move. So don't be fooled by such diagrams where it's shown in like in blue. Essentially, these are rock bodies which carry water because of their porosity. So yes, we also have answers in the chat. So that will be our answer A. So the next question is underground water sources include springs, wells, infiltration wells, or all of these. Again, any answers?
All of these, I guess.
All of these. Any answers in the chat box? Yeah, I mean, they are all underground water sources. We can, this is a very basic picture. So I want to talk about one thing here. So you can see how this spring formation, so this part, I think you can't see it. So this part here is also covered, right? So what happens is, this is the interflow we are talking about. It's similar to interflow. It's not necessarily interflow. So what happens is, say the rain falls and then it seeps in here, and then it starts flowing because the gradient of the hydraulic gradient, as you must have seen in the lectures, is in this direction. So water starts flowing towards this end, but the soil basically dips further than that. So what happens is, if there is an opening here, water will start gushing out without any need for digging or anything. These are essentially springs. In case of surface bodies, say the water table is very close to the surface, and there is a, or rather above the surface, and there is a crack, those are called artesian wells. So there is a vertical formation, spring is just, they're just complementary formations to each other. So you can see that this is an aquifer. It's not purely water. So it's a rock with a lot of gaps in it, porosity of different sizes, um, which is called the aquifer. Right. So I think that will be the end of our session this week. I hope it was useful, especially with the numericals, because yeah,
Yeah, I have one question.
yes, yes, please.
It's not related to anything problem solving. Like I'm enrolled in both two courses, that is transportation planning and utilities one. So
Yeah.
to whom should I contact or mail for having different dates of exam, or maybe 1 week of difference for both the exams?
Oh, okay. So you're enrolled in both, but the exam dates are clashing.
Yeah, it's on the same date. I think 22 October, or
Okay.
I
If
forgot.
I'm
I
not wrong, I think there are two slots that you can opt for. Like there is a morning slot and there is an evening slot. But if you need the date to be sort of shifted, I don't know if it is even possible. If I'm
Okay.
if I'm not wrong, it's scheduled by the NPTEL team. So what you can,
Okay.
however, do is raise the issue in the discussion forum, where it will be
Where
addressed very immediately by the main TAs of the NPTEL. I will also raise it to them personally. I do know them.
yeah, please thank.
Yes,
And
yes.
so where did you told me to raise the query? Like which is the discussion forum?
So there is a discussion forum.
Yes.
Yeah. So if you go to your NPTEL homepage, you can
Yeah.
see this Ask a Question tab.
Okay.
That's
All right.
where, yeah. So that's where you will find.
Okay.
You can raise your. You can just post a new conversation and raise the issue.
Yeah. Yeah. Okay. Okay. Thank you.
Yeah. So, can you provide recorded backups? It is available, Shripad. I think it was shared even in via mail to all the participants. But that being said, I think again 1 second, I will just share my screen again. I can show it to you where it is. So if you go to your NPTEL homepage, you will see this problem solving session tab. In this, if you go, there is a list of, you can download the PDFs of the lecture sessions. So there are two TAs who are handling these sessions. So there is one session tomorrow as well. To those of you who know about it, all our recordings will be available here, and this will be the presentation folder link also. So you can download the PDFs as well for reference. So two sessions. Yes, yes, Anurag. That's precisely what I told Ms. Supriya also. There are two sessions, but I think it's more about preparation time. So I will raise the issue with the NPTEL course team, but the main team might not be able to address the issues. Any other queries? Okay, Ashwin, I will check the answers. I haven't gone through the current week's assignment. I have verified the previous run's answer key. So, in case there is a discrepancy, I will post in the discussion forum as well. Please an eye on it. I will either I will post or I'll ask the main NPTEL team. If there is no clarification coming from our side, it means that you might be going wrong somewhere. So, yeah, thank you. All right, I think we'll close the session for today. If you have any other queries, any other issues, you can post in the discussion forum. You're very welcome to raise them. Or if you would like the interaction sessions to be slightly different, you can raise that as well. Me and Jaslu have slightly different ways of taking class. So whichever you're comfortable, you can join that. So I don't usually write and explain because I just don't have the equipment to do so. So, but usually the questions are almost the same. We wouldn't be. You don't have to attend both sessions. In case I think you have to attend both sessions, I will let you know here. All right then. Once again, happy Independence Day. Have a good day, all of you. And have a good week ahead. Until next week.